So hi guys, good morning. Am I audible to all of you guys? Am I audible? Hello.
Yes, sir.
Okay, fine. Okay, I hope the screen is visible to all of you. So in the last class, what I was talking about is I was talking about the synthesis of a composite catalyst. So when we talk about a composite catalyst has got two parts. So first part is the active metal part and the second part is the support part. So in the last class, I talked about how can one pre-treat the support, since we're not going to prepare the supports in our lab or in the it from some means companies like Alpha SR, Sigma, Aldrich, Loba Chemi. There are so many other companies as well. So we procure the support material. So whatever support material you procure from these companies, they are highly impure in nature. Okay, so unless these support materials are pure, we cannot use this support material for the catalyst preparation. Since catalyst means active metal part dispersed on the surface of a support material. So if it is impure, then one has to purify the support before synthesizing the catalyst. So how can we purify the support material? So support material is, first of all, we make a mixture of support and H2O and we mix them thoroughly to form a paste. And after that, we transfer this paste in a muffle furnace operated at a temperature of around 550 degrees Celsius for 4 hours under air atmosphere. If our support is, see here, the support we are talking about are basically non-carbonaceous in nature. If the support is non-carbonaceous in nature, then we don't need to use any inert atmosphere. If we have got carbonaceous support material, then one has to provide an inert atmosphere like nitrogen atmosphere, helium atmosphere, argon atmosphere, etc., etc. So what happens is, muffle furnace, we carry out the heat treatment at a temperature of around 550 degrees Celsius for 4 hours. And as a result, removal of volatile impurities and entrapped gases inside the support material take place. And finally, after 4 hours, we allow the muffle furnace to cool down to room temperature. And the moment it reaches the room temperature, what we do is we take out the support material. Okay, so the support material, what we obtain at room temperature, that is in the lump form. Okay, but lump means support material we cannot use, since if we use a lumpy material, then what will happen is there will be less active sites available for the active metals to be deposited on. So in order to avoid that, what we do is, whatever solid lumpy material we obtain from the muffle furnace, we either go for ball milling operation or motor and pestle. Okay, so suppose we are handling 1 gram of the support material, then we will go for the motor pestle operation. Otherwise, what we will do is, suppose we are having 100 gram of solid lumpy material. So then we will go for the ball milling. So fine grinding will be taking place, and as a result, we will end up with fine powders. So these are basically the support material in the purest form, and that too in the powder form. Okay, so by these operations, we get support material in pure form. That means 99.99% pure support material in the powder form we can obtain. Okay, so this is our first goal. The second goal would be to incorporate the active metals on the surface of a support material. So these are fine powders, remember this. Okay, so what we do is we will do impregnation method. Sometimes this method is also called as incipient wetness impregnation method. Okay, in this method, what we do is, let's assume we are going to incorporate nickel metal on the surface of a support. So what we will do is we'll use a precursor, nickel precursor salt. So what could be our typical nickel precursor salts? It could be either nickel nitrate, nickel sulfate, okay, nickel carbonate also we can use, or nickel acetate also in some of the cases people might use. So what we will do is we'll first perform the impregnation operation. Impregnation operation means dispersion of this nickel nitrate salt onto the surface of the powder support material. Okay, so how can we incorporate nickel nitrate onto our support? First of all, we'll make a liquid solution of or aqueous solution of nickel nitrate. Okay, so nickel nitrate salt, that means nickel nitrate hexahydrate will be first mixed with certain amount of H2O, okay, to form a aqueous solution of nickel nitrate. So let's assume I have taken 1 gram of the support material. So whenever we synthesize any catalyst, we'll have to take a basis like 1 gram of the support material. So all the calculations will be performing on the basis of 1 gram of support material. Okay, so we have got 1 gram of support material. We are allowing impregnation method to incorporate nickel nitrate onto the surface of this support material. And the support material is in the powder form. Remember this. So as a result, what will happen is nickel nitrate salt will get deposited onto the surface of a support material by this method. But our objective would be to get nickel on a support material. So nickel on a support material is our catalyst. But remember, now we have nickel nitrate. Okay, so now what we'll be doing is our goal would be to convert this nickel nitrate into elemental form. That means nickel with 0 oxidation state. In nickel nitrate, nickel has got +2 oxidation state. Since we all know that nitrate anion has got 1 oxidation state, so there are 2 nitrate anions are associated with 1 nickel atom. So here -2, then nickel means there has to be +2 in order to nullify this. Okay, so the overall oxidation state should be 0. So nickel has to be +2. Since we have got 2 nitrate anions over here, so nitrate anion has got -1 oxidation state. So -1 multiplied by 2, that gives you -2. So it has to be +2. So in nickel nitrate, nickel has got +2 oxidation state. However, our catalyst is nickel on the support. That means nickel has to be in the 0 oxidation state. So how can we accomplish this? So there has to be 2 different ways, right? So first of all, what we'll do is we'll decompose this nickel nitrate into nickel oxide. That means NiO. In the next step, what we'll do is we'll reduce nickel oxide thus produced in the first step into its elemental form. That means nickel on a support. So this would be our catalyst. So let me go one by one. So the first operation to convert nickel nitrate into nickel oxide is called the calcination operation. If you remember, I talked about the calcination reaction while teaching you the 23 major reactions in the petroleum, in the different refineries, or not refineries, different industries. So first of all, calcination operation. Remember, this support material is non-carbonaceous in nature. That means it could be either alumina or silica alumina or silica or zeolite or molecular sieve, zirconia, so on. Okay, so calcination operation will perform in the air atmosphere. Air atmosphere means oxygen atmosphere we are talking about. Okay, so in the air atmosphere will perform calcination, means the calcination operation will be performed in a muffle furnace at a temperature of around 500 degrees Celsius for 4 hours. Here we cannot choose our calcination temperature, means without performing any analysis or something. These are all optimized conditions. Okay, always remember this. So there is a process called temperature program reduction analysis. We carry out this analysis to calculate or to obtain the optimized calcination temperature. So I have already done this kind of studies, so I know the optimum calcination temperature would be around 500 degrees Celsius. Okay, so following the calcination operation, we ended up with a compound called nickel oxide on a suitable support, that too in the powder form we need, right? But the moment we have done these operations, so again we'll end up with a lumpy material. So we'll go for the ball milling operations to make it into powder form. Here I have by mistake I have written power form, so it would be powder form. Okay, so by ball milling operation, lumpy materials, that means nickel oxide on a suitable support, will be transformed into a powder, into its powder form. So remember, now we have got powder that is made up of nickel oxide on a suitable support. So how can we convert this nickel oxide into this nickel? So reduction operation has to be performed. Reduction can be performed in several ways, like liquid phase reduction operation. Even gas phase reduction operations are also being performed. But in catalyst preparation, people generally go for the gas phase reduction. Gas phase reduction means at a certain temperature, will allow hydrogen gas to pass through the material. So the moment the hydrogen gas will come in contact with these oxides, it will produce H2O. That means steam will be generated and nickel oxide will reduce to nickel. So this reaction is called the reduction reaction. So reduction reaction we perform in a horizontal furnace. This is called a horizontal tubular furnace. So in the furnace we have got one SS made tubular reactor. So this tubular reactor is mounted inside the furnace, and the reduction reaction is also performed at a temperature of around 550 degrees Celsius for around 4 hours. Okay, again, the 550 degrees Celsius I cannot choose by myself. There are several methods to optimize the optimum reduction temperature. Okay, so the method is, again, the method is called the temperature program reduction analysis or TPR analysis. This is very famous reaction for catalyst preparation. Okay, so what we will do is reduction operation will performed in a horizontal furnace, and inside that furnace there is a means tubular reactor. So tubular reactor is made up of high grade SS. Sometimes this is called as inconel reactor, INCONEL. Okay, inconel reactor. Inconel reactor means high grade stainless steel made reactor. Okay, so the reaction is being conducted inside this tubular reactor at a temperature of around 550 degrees Celsius for 4 hours. So as a result, we ended up with a compound called nickel on a suitable, dispersed on a suitable support. So this is our final product or the main catalyst. Okay, so this is how we can synthesize a composite catalyst. This is very important thing. You need to remember this. Okay, so here I am teaching you how to synthesize nickel on a suitable support. Maybe in the exam, I'll ask you to write down the steps involved in the synthesis of platinum nanoparticles or rhodium or palladium nanoparticles dispersed on a suitable support. Means for that, you will have to understand what type of precursor salt you will be using. Means now you can understand, since we are going to incorporate nickel on a suitable support, so we are supposed to use a nickel precursor. So what could be our different nickel precursors? It could be either nickel nitrate, nickel sulfate, nickel carbonate, nickel acetate. Similarly, for platinum, palladium, rhodium, we need to use certain precursors. For platinum, a very famous precursor salt is H2PtCl6, that means chloroplatinic acid. H2PtCl6, chloroplatinic acid. Similarly, I want you to find out what would be our typical precursor salts for rhodium and palladium based catalyst. Let's assume we are handling a transition metal based catalyst. Here I have taught you how to synthesize nickel. So maybe I can ask you how to synthesize iron nanoparticles, okay, or cobalt nanoparticles dispersed on alumina. So for that, you will have to use iron nitrate, that means ferric nitrate nonahydrate FeNO3 whole thrice dot 9H2O, or ferric carbonate or ferric acetate. Okay, so these are the precursor salts we will be using to synthesize iron based catalyst. Similarly, for cobalt based catalyst, we will be using cobalt nitrate, okay, cobalt sulfate, cobalt carbonate, cobalt acetate, like that. Okay, so I hope this part is understandable to all of you. In the last class also I talked about these things. So today it was just a recapitulation. So now coming to the two important properties. However, means every catalyst has got several features or characteristic features, but there are two different characteristic, more important rather, characteristic features are, one is surface area and pore size distribution. Okay, and the second one is the acidic surface sites. When I will talk about the petroleum refinery processes, then you will understand how does active surface area play a major role in such catalytic reactions. Similarly, the acidic surface sites also has got a crucial role to play in a catalytic process. Okay, so for that, you need to understand what do we mean by surface area and pore size distribution, and the secondarily we need to understand what is acidic surface sites. So first of all, let's go one by one. So first of all, let's talk about the surface area and pore size distribution. Okay, so we can measure this thing by a method called BET, surface area and pore size distribution analysis. Okay, BET is named after three scientists. So they are Brunner, Emmett, and Taylor. Okay, so there are three scientists. So this method is named after these three scientists. Okay, So here we measured the overall surface area of the material. Surface area is based on the pores, okay, amount of pores available on the surface of a entire catalyst or on the surface of the support material. Since whatever active metals we are depositing on the surface of that support material, they are not that much porous. Most of them are non-porous, means they have got very low surface area, like 5 meters square per gram or something like that. Before means going into the detail of this thing, let me tell you that the surface area will determine in terms of meter square per gram of catalyst. Okay, so surface area would be meter square per gram of catalyst. So our basis is 1 gram of catalyst. Okay, and the method is called BET method. That means Brunner Emmet Taylor method. So surface area means when we talk about the surface area of a catalyst, so we talk about the surface area of the support plus surface area of the active metal. However, what we have realized is surface area of the active metal is not that much. It has got max to max surface area of around 10 meters square per gram. However, based on but the surface area of a catalyst is dependent on the type of support material we are using. Let's assume we are using a non-carbonaceous support material. So in such case, non-carbonaceous support material like alumina. Means there are two different forms of alumina available in the market. So one is alpha alumina, another one is gamma alumina. One has got surface area around 50 meters square per gram. The another one has got a surface area of around 200 meters square per gram. Okay, silica also has got similar type of surface area, like it's close to 200 meters square per gram. However, if we are handling silica alumina based catalyst, then silica alumina has got a surface area of around 400 meters square per gram. Let's assume we are using zeolite based catalyst. So zeolite has got very high surface area. Very high means around 700 meters square per gram. Okay, let's talk about now let's talk about the surface area of carbonaceous materials. Let's assume we are working with activated carbon fibers. So activated carbon has got a very high surface area, though the surface area of activated carbon depends on the type of synthesis route. Okay, so based on the synthesis procedure, the surface area of activated carbon varies. Okay, so the surface area of activated carbon may range between 500 and 1400 meters square per gram. Generally, activated carbon has got a very high surface area, but there are several operational difficulties with activated carbon-based materials. That's why in most of the reactions, we don't use or we don't prefer to use activated carbon as a support material. Since what will happen is if we are handling activated carbon, then we are limited to a certain temperature. That means we cannot carry out the reaction beyond 400 or 450 degrees Celsius. So at that temperature, what might happen is activated carbon, we have got like activated carbon will burn off in the form of carbon monoxide and carbon dioxide. That's why people are generally using non-carbonaceous support material to avoid such burn off issue. Okay, since non-carbonaceous material has got high melting point above 1000 degrees Celsius, so burn off issue is not there, okay, with the non-carbonaceous support material. Now coming back to the BET surface area and pore size distribution analysis. So here BET surface area and pore size distribution analysis we perform. First of all, in order to perform this test, we take a quartz tube. Okay, so here I have tried to draw a quartz tube, and inside that quartz tube, we take certain amount of catalyst material. Let's assume we have taken 40 milligram of the catalyst material inside this quartz tube. And this quartz tube is immersed inside liquid nitrogen. So now the question comes, why do we need to use liquid nitrogen here? Since we all know that liquid nitrogen has got very low temperature, right? So it has got a temperature of around 77.35 Kelvin, and adsorption facilitates at low temperature. We all know this. So what we'll do is this method, like BET surface area and pore size distribution analysis, this method is sometimes or most of the times it is called as physisorption method. Okay, there are two different types of adsorption, like one is physisorption, another one is chemisorption. Hopefully in chemical reaction engineering you have studied this. So this process is called the physisorption technique. So in physisorption technique method, in physisorption technique, what we do is we use certain physisorption probe gas. So here our physisorption probe gas is nitrogen. Okay, it is universally accepted physisorption probe gas. In some cases, we can use carbon dioxide also as a physisorption probe gas, but again, this is dependent on the type of catalyst material we are using. Okay, but in most of the cases, nitrogen is used as a physisorption probe gas. Okay, so here what we do is we take a quartz cell. Inside this quartz cell, we take around 40 milligram of the catalyst, and this is immersed in liquid nitrogen bath. Okay, so the bath temperature is around 77.35 Kelvin, and at that temperature, what we do is we allow this nitrogen gas to flow through this catalyst material. So as a result, what will happen is the moment this nitrogen will come in contact with the catalyst particle maintained at a temperature of around 77.35 Kelvin, nitrogen gas molecules will get attached to the surface of this catalyst material. So this is a weak van der Waals force of interaction. Since there is no chemical bond formation taking place, right? In physisorption, it's like a weak interaction between the adsorbate and the adsorbent. Adsorbate means the substance which is getting adsorbed onto the surface of a solid material called adsorbent, right? So here our adsorbent is the catalyst particle, and what is our adsorbate here? Adsorbate is the physisorption probe gas, that means nitrogen. Okay, so in BET method, there are several assumptions. Let me talk about these assumptions one by one. Hopefully you remember for Langmuir adsorption isotherms, we have got monolayer coverage of adsorbate over the surface of over the homogeneous surface sites, isn't it? But in case of BET surface area measurement, we take certain assumptions like we have got formation of multi-layers, okay, instead of forming the monolayer. That means here you can see multi-layers, like this is layer 1. These are all nitrogen gas molecules, and this is our support or the catalyst material that is called as the adsorbent. And this is this round shaped or spherical shaped particles are basically the adsorbate. So in this case, our adsorbate is nitrogen gas, right? So here what happens is how many layers one can see over here. So here this is layer number 1, this is layer number 2, this is layer number 3, this is layer number 4, and this goes on. Okay, so that is why we are saying that in BET adsorption method we have got multi-layer formation of adsorbate over a homogeneous surface sites. It could be either homogeneous or heterogeneous, it doesn't matter in case of BET. However, in case of Langmuir adsorption isotherms, we have got monolayer coverage of adsorbate over the homogeneous surface sites. Okay, so here multi-layer absorption is taking place in BET, and side by side there will be no interaction between two adjacent molecules. That means this molecule won't interact with this molecule. Again, this molecule have got no interaction with this one, and the same is applicable for these two molecules as well. And this is also valid for all other layers as well. Okay, so that means we have got two major assumptions for BET method. In BET method, there will be multi-layer formation of adsorbate over the surface of either homogeneous or heterogeneous catalyst surface. Second, there will be no physical interaction between the molecules in a single layer. That means two adjacent molecules won't interact with each other. So this is applicable for this molecule, this and that molecule, and the same thing is valid for all other layers as well. Okay, so this was all about the BET method. So roughly, you know, we have got a quartz tube. Inside this quartz tube, we have taken around 40 milligram of the catalyst, and this is immersed inside a liquid nitrogen bath maintained at a temperature of around 77.35 Kelvin, and we are allowing nitrogen as a physisorption gas to flow through it or to penetrate through it. The moment this nitrogen will come in contact with the catalyst at 77.35 Kelvin temperature, there will be physisorption. That means weak force of interaction will be there between these means gas molecules and the surface of the catalyst. Okay, so there are 5 different types of adsorption isotherms, BET adsorption isotherms. Here I have shown only 2. So this is type 1 adsorption isotherms. That means here monolayer coverage of adsorbate is taking place. Okay, so this is called the single layer adsorption is taking place. And after a certain while, it happens means here volume of the gas adsorbed increases with increasing P by P naught. Here P is the pressure. Okay, pressure ranges between 0 to 760 millimeter Hg, while P0 is called the saturation vapor pressure, that is basically 760 millimeter Hg. So here the range of P by P naught would be between 0 and 1. Okay, and here along y-axis we have got volume of the gas adsorbed. Volume of the gas adsorbed means volume of the nitrogen in this gas. Okay, so nitrogen adsorbed. And what would be its unit? This unit would be cc per gram. Always remember, when we talk about the surface area, it will be in terms of meter square per gram, while when we have taken gram is basically the weight of the catalyst. So it is performed on the basis of 1 gram of catalyst. Similarly, how can we determine the volume of the gas adsorbed? Again, it has got a basis of 1 gram of catalyst. So volume of the gas adsorbed has got a unit of cc per gram. So along y-axis we have got volume of the gas adsorbed in cc per gram, and in the x-axis we have got relative pressure. Why is it called relative pressure? Since it's the ratio between two pressures. Like one is pressure, means system pressure, that ranges between 0 and 760 millimeter Hg, and P naught is basically the saturation vapor pressure, that means 760 millimeter of Hg. So here P by P naught has got a range between here 0 to 1. So from this type 1 isotherm, what we can make out is the volume of the gas adsorbed with increasing P by P naught value up to a certain level, and after that it levels off. See, here it has levels off, and here volume of the gas adsorbed, that means at low P by P naught value we have got means increased volume of the gas adsorbed. After a certain point, what will happen is it will level up. That means there will be not much increase in the volume of the gas. Okay, and after a while there will be little bit increase in the volume of the gas adsorbed, which you cannot see from here. Okay, so this is a typical type 1 adsorption isotherm. So type 1 adsorption isotherm is valid for activated carbon based materials. Like suppose we are using activated carbon fibers, activated carbon, okay, activated carbon microbeads. For those materials, the type 1 adsorption isotherm is valid. Okay, so let me tell you again. So this is type 1 adsorption isotherm. So along the x-axis we are plotting the relative pressure. That means a ratio between P by P and P naught. So P is the system pressure that ranges between 0 and 760 millimeter of Hg. P naught is basically the saturation vapor pressure. That means 760 millimeter Hg. So the P by P naught has got a range between 0 and 1. It is unitless since it's a ratio of two pressures, right? So millimeter of Hg, millimeter of Hg, they cancel out each other. So it doesn't have any unit. However, along y-axis, we are plotting volume of the gas adsorbed. So what would be its unit? The unit would be cc per gram. So here also we have got a basis. What is our basis here? 1 gram of catalyst. So cc per gram is used. So here it is 0, and here the maximum P by P naught value is 1. So at low pressure, the volume of the gas adsorbed at a certain up to a certain level like this, and after that what happens is it levels off. That means there is not much variation in the volume of the gas adsorbed, and at very high P by P naught value, that means close to 1, there will be marginal increase in the volume of gas adsorbed. Okay, so this is a typical type 1 isotherm. Okay. So this type of adsorption isotherm is valid for activated carbon-based materials. So what would be our activated carbon-based materials? It could be either activated carbon fibers, or activated carbon microbeads. Okay, so let's talk about another type of isotherm. This is basically type 4 adsorption isotherm. So here you can see is always there will be increase in the volume of the gas adsorbed with increasing P by P naught value. So here also, along x-axis we are plotting P by P naught, and along y-axis we have got volume of the gas adsorbed in cc per gram. So here always we can see the increase in volume of the gas adsorbed with increase in P by P naught values. Okay, so this is typical type 4 isotherms. For carbon nanofibers, carbon nanotubes, we can see this kind of adsorption isotherms. Okay, so always remember this. So while talking about the surface area, okay, so let's assume we have got BT surface area. So BT surface area means we have got the entire surface area of that material. Means of that catalyst. But always remember, all the surface area available on the surface of that catalyst material is not active for a reaction to take part. Okay. So out of, let's assume I have got 100% surface area. Out of 100% surface area, maybe only 10% surface area is active for the catalytic reaction. Remaining 90% surface area is not that active. That means not active or non-active means on the surface, active means on the surface of that part, the chemical reaction is taking place. Active means the part of the catalyst surface that is responsible for the catalytic reaction. Inactive part means there will be surface area where there will be no reaction. Okay, so it's basically a surface area on which there will be no reaction taking place. So this is the inactive part of the surface area. So always remember, by BT surface area analysis, we get a surface area. So this surface area corresponds to the overall surface area of the material. Okay, however, out of overall surface area, some very minimal amount of surface area is available for catalytic reaction. So this is called as active surface area. Let's assume I have got 100% active 100% surface area. Okay, so out of 100% surface area, maybe 5 to 10% surface area is responsible for the catalytic reaction. So this 5 to 10% surface area will be treated as the active surface area. Similarly, remaining 90 to 95% surface area is not active or not available for the catalytic reaction. So that 90 to 95% surface area will come under the inactive surface area of the catalyst material. Always remember this. So the active surface area of the catalyst is responsible for the catalytic reaction. Okay, so now determination of surface area and pore size distribution. Just now I have talked about the procedure, okay, that we carry out in order to calculate the overall surface area of a catalyst material. So it will always be calculated in terms of meter square per gram. Okay. So now coming to the pore size distribution, I have already talked about these things like type 1 isotherms. Okay, so high BT surface area. What are the materials that can come under type 1 isotherms? Okay, I have talked about this. That's why I'm not repeating this part again. P by P naught ranges between 0 and 1. I have already spoken about those things. Now moving on to the pore size distribution analysis. This is very important. With the same analysis like BT surface area and pore size distribution analysis is very important with regard to the catalytic reactions. Or suppose we have synthesized one catalyst, until and unless we perform this analysis, we can't conclude anything about that catalyst. Okay, so now coming to the pore size distribution. Probably most of you know that there are 3 different types of pores available on the surface of a catalyst materials. Okay, so one type of pore is called the micropore. The second type of pore is called the mesopore, and the third type of pore is treated as the macropores. So let me tell you the dimension of each type of pores. Okay, but before telling this, let me tell you the surface pore volumes we calculate, right? So micropore volume is calculated in terms of cc per gram. Similarly, mesopore volumes also we calculate in terms of cc per gram. Okay, macropore volume is also calculated in cc per gram. Okay, so now coming to the dimensions of micropores. So this is based on the IUPAC norms. Okay, always remember this. So when we have got pore diameter less than 2 nanometers, that will come under the micropores. Okay, so that means we have got very small pores. These pores are basically called the micropores. Carbon-based materials are mainly microporous in nature. Like in such case, it will follow the type 1 absorption isotherm category. Okay, so micropore means we have got pore diameter. Always these things will be classified in terms of the pore diameter, right? So in case of micropores, we have got pore diameter that is less than 2 nanometers. Okay, so what type of materials exhibit micropores? So activated carbon-based materials always have the majority micropores. Okay, so it has got preponderance of micropores. And the second type of pore is called the mesopores. So mesopore, in case of mesopores, the pore diameter ranges between 2 and 50 nanometers. Okay. Similarly, for macropores, the pore diameter is greater than 50 nanometers. So in case of mesopores, means mesoporous materials are basically means alumina, silica alumina. Okay, these are the materials, they come under the mesoporous material. Mesopores means they have got majority of the pores ranging between, with dimension ranging between 2 and 50 nanometers. For activated carbon-based materials, pore diameter is very small, that is less than 2 nanometers, and these are treated as the micropores. However, for mesopores, the pore diameter range between 2 and 50 nanometers. Okay, so activated in case of mesopores. So what are the materials that exhibit the mesopores? So the materials are alumina, silica alumina, sometimes zeolite also exhibit the mesoporous nature. Okay, and for macropores means you have got a huge amount of pores, like with pore diameter greater than 50 nanometers. Okay, there is no as such no classification of mesoporous macroporous materials. So how do you calculate the macropores? Actually, the BET method doesn't calculate the macropore volume. So macropore, it gives us the total pore volume and micro and mesopore volumes. Okay, so total pore volume, let's assume I have got like 1.20 cc per gram as total pore volume, and micro and mesopore volume also we know. So how can we calculate the macropore volume? So 1.26 minus summation of micropore volume plus mesopore volume. So by this formula, we will calculate the macropore volume. I'm repeating again. Let's assume I have got, before telling it, let me again tell you that by BET method, we don't calculate the macropore volume. So macropore volume we calculate based on the subtraction, okay, method. So how can we do so? The BET method will give us the total pore volume. So we already know what would be our total pore volume. Micro and mesopore volume we can also get from the BET absorption isotherm method. So micro mesopore volume we know. We'll take total pore volume minus summation of micropore volume plus mesopore volume will give us the macropore volume. Okay, so by this we'll calculate the that means the by back calculation we'll calculate the macropore volume. Okay, so this was all about the BET surface area and pore size distribution analysis. Okay, I'm not going into the detail of it. It's very complicated, and also we don't have much time to explain those things. So whatever I said, you just remember this. For a UG level, this is more than sufficient. Okay, when I'll teach these things in MTech and PhD, then I will talk about those things in detail. But whatever I said just now, you always remember this. So this would be sufficient in the undergraduate level. Okay, so next coming to another very important characteristic feature of a catalyst, this is called as the surface acidity. Also surface basicity also we always calculate. Okay, so this surface acidic property will help in cracking reactions. Okay, when I'll talk about the hydrocracking reaction, I'll talk about the surface acidity. But before that, you need to know what is surface acidity. Surface acidity means we have got surface area, right? So by now, things are clear to you that we have got surface area. Out of 100% surface area, very minimal part of surface area is active for a catalytic reaction. So this is treated as an active surface area or surface sites. In catalytic reaction, we talk about the surface sites. Okay, so I'll talk about surface sites instead of talking about the surface area. Okay, so by now you know what would be our active surface sites, what would be our inactive surface sites. Inactive surface sites, there will be no catalytic reaction taking place. Now I need to calculate the acidic surface sites present in our catalyst material. Okay, so acidic surface sites eventually helps in various reactions, like it helps in the cracking reaction. Okay, it helps in the hydrocracking reaction. In reforming reaction also, acidic surface sites play a major role. Okay, so now let's talk about how can we calculate the acidic surface sites present in a catalyst material. Okay, so there is a famous technique to calculate the surface acidity or acidic surface sites present on a catalyst material. So the process is called temperature programmed desorption analysis, or most famously called as TPD analysis. Let me talk about it again. So let temperature programmed desorption analysis, or more specifically TPD analysis. So in this method, what we do is Okay, we'll use ammonia as a TPD probe gas. Okay, why do we need to use ammonia here? But before telling you this, let me tell you. So when we want to calculate the acidic surface sites, we'll incorporate one basic gas into the system. However, when we want to calculate the basic surface sites, then we will incorporate one acid. So when we want to determine the acidic surface sites, then we incorporate or we purge ammonia through the system. Okay, that means we allow ammonia to interact with the catalyst material to determine the acidic surface sites. Similarly, to determine the basic surface sites, we allow, instead of ammonia, we use carbon dioxide, since carbon dioxide is slightly acidic in nature. Okay, so that means for determination of acidic surface sites, we'll use ammonia, while for the determination of basic surface sites, we'll use carbon dioxide, okay, as a probe gas. So here, now our objective would be to determine the acidic surface site. So how can we do so? By a method called temperature program desorption analysis, or more specifically TPD analysis. So we have got a U-tube cell here. This is quartz made. Okay, and this is mounted inside a furnace operated under PID mode. PID mode means proportional integral derivative mode. Okay, so we have got a furnace, we have got a quartz U cell rather. So inside this we put around 100 milligram of the sample, and we allow the furnace temperature to increase from room temperature to 950 degrees Celsius. Okay, so temperature ramp we need to use. We are using a temperature ramp of 10 degree per minute. So this can be accomplished when we use PID mode. PID means proportional integral derivative mode. So first of all, we carry out the reaction. So how can we do so? First of all, let's understand this. So we have got a U-tube, we have got room temperature. Okay, so the U-tube U cell is mounted inside this furnace. Okay, and the furnace temperature can be regulated with PID temperature controller. Okay, so first of all, what we will do is we will allow ammonia to purge through this catalyst material at room temperature. Why at room temperature? Since if the temperature is lower, then this will facilitate the adsorption process. Okay, so first step is the adsorption, and the second step would be the desorption. Okay, adsorption, desorption, we all know, right? What is adsorption? You know. What is desorption? That is also known to you. So at room temperature, we will perform the adsorption operation. However, desorption will be studied as a function of temperature. So how would we increase the temperature from room temperature? Let's assume our room temperature is around 30 degrees Celsius. So we will increase the temperature of our system, like from room temperature, that means from 30 degrees Celsius to 950 degrees Celsius at a temperature ramp of 10 degree per minute. That means at 1 minute there will be 10 degree increase in the furnace temperature. Okay, so what we'll do is we'll allow the furnace temperature to increase from room temperature to 950 degrees Celsius at a temperature ramp of 10 degree per minute. As a result, what we'll record the signal with a TCD detector. Okay, so TCD detector will detect, TCD detector means the thermal conductivity detector. Okay, so the thermal conductivity detector will detect the dissolved gas. So what will be our dissolved gas here? Here our adsorbed gas was ammonia, so dissolved gas will also be ammonia. So desorption will be carried out from a temperature between room temperature and 950 degrees Celsius. However, we first of all we perform the adsorption study at room temperature. Let's assume ammonia at a flow rate of 10 ml per minute was purged inside this quartz cell. Okay, purged inside this quartz cell means this ammonia was made in contact with these catalyst particles. These are all in powder form. Sometimes we can make powders into pellets, and these pellets can also be incorporated inside this U-tube. However, while the reaction is over, it is very tedious to take out the pellet material. So that's why generally people use powder material, and we block these two ends by quartz wool. Okay, so we carry out the desorption operation. So we are carrying out the desorption operation as a function of temperature. Okay, so here our temperature, like it is temperature increases along this way, and this is our TCD signal. So TCD signal will be recorded in terms of millivolt. Okay, and desorption will take place. So dissolved gas will be ammonia, since here we allowed ammonia to absorb. So what will be our dissolved gas? So the ammonia would be our dissolved gas. So we'll get at three different peaks of desorption. That means desorption of ammonia. These three peaks, like at low temperature, at intermediate temperature, and at high temperature. There will be three different peaks, right? So at low temperature, so the peak would be like desorption of ammonia. So low temperature means around 100 to 150 degrees Celsius. Intermediate temperature means temperature between 300 to around 300 to 450, max to max 500 degrees Celsius. What would be treated as the high temperature? High temperature means beyond 500 degrees Celsius. That means 500 to around 950, even 1000 degrees Celsius also comes under the high temperature. Okay, so here you can see three different peaks at three different temperature regions. So the first peak corresponds to the desorption of ammonia at low temperature. The second peak also desorption of ammonia at intermediate temperature. And the third peak also corresponds to the desorption of ammonia at high temperature. Okay, so the low temperature peak is treated as the strong acidic surface sites. Okay, always remember this: when we have got strong acidic surface sites, that will respond at very low temperature. So this will be treated as the desorption of ammonia gas at low temperature. So this would be treated as strong acidic surface sites. So when we have got intermediate acidic surface sites, that will means we'll get the peak at an intermediate temperature. So intermediate temperature peak, intermediate means acidic surface sites peak will be obtaining at intermediate temperature. However, weak acidic surface sites will be obtaining at a high temperature. That means we have got weak acidic surface sites, intermediate acidic surface sites, and strong acidic surface sites. Strong acidic surface sites respond at a very low temperature. Intermediate acidic surface sites respond at intermediate temperature. Similarly, the weak acidic surface sites. Okay, so we'll get weak acidic surface sites at high temperature. Always remember this. Here I have also written down different surface acidic sites. So strong acidic surface sites at low temperature, intermediate acidic surface sites at intermediate temperature, and finally low acidic surface sites at high temperature. So here, let me explain this again. So we have got a U-tube. Okay, this is quartz made. Okay, so this is mounted inside a furnace maintained at a temperature of around 30 degrees Celsius. That means at a room temperature. But we have got a provision to increase the temperature of this furnace from room temperature to a certain temperature, like around 950 degrees Celsius, by a PID controller. PID controller means proportional integral derivative controller. Okay, so why do we need this? We need this to increase the temperature. We cannot abruptly increase the temperature at certain ramp, right? So there has to be a certain ramp for that. So what is our ramp? That means it is 10 degree per minute. In some cases, people uses 20 degree per minute as well, but not above 20 degree per minute. Okay, so from room temperature to 950 degrees Celsius. Okay, so at a ramp of 10 degree per minute. Okay, using ammonia as a TPD probe gas. So first of all, we will perform the adsorption study. So adsorption will be performed at room temperature. That means at around 30 degrees Celsius. Let's consider our room temperature is 30 degrees Celsius. Now what we'll do is we'll allow that desorption to take place. Adsorption followed by desorption. But desorption cannot be taking place at low temperature. So how do we record the desorption peaks? We'll record the desorption peaks as a function of temperature. That means we'll increase the furnace temperature from room temperature to a certain temperature, let's assume up to 950 degrees Celsius. So we'll have three different peaks at three different locations, temperature locations rather. And these peaks will be detected by a detector called thermal conductivity detector. So this detector will record the signal in millivolt. Okay, so there will be three different peaks at three different temperature regions. So the first peak corresponds to the desorption of ammonia gas at low temperature. So this is treated as strong acidic surface sites. Similarly, there will be another peak at intermediate temperature. This would be also corresponding to the, or this would be attributed to the desorption of ammonia gas. So this would be considered as intermediate acidic surface sites. Finally, at high temperature, there will be another desorption peak for ammonia. So this is high, that means this is the low acidic surface sites. So we have got three different acidic surface sites over here. Okay, so this is one is strong acidic surface sites at low temperature, intermediate acidic surface sites at intermediate temperature, and finally low acidic surface sites at high temperature. Okay, so we don't have time now, so it's like 10:55. So I will continue from here on Wednesday. Okay, so if you have got any doubts, you can put forward those things to me on Wednesday's class. Okay. Okay, so thank you guys.
Thank you, sir.
Thank you.